Hello, everyone, and today we're going to discuss another extension for the Adams optimizer algorithm. And just quick review what we had for the Adams algorithm before. In Adams algorithm, we keep two different type of a momentum, and first we call it first order momentum. And the S represents the second order momentum. And basically, one of is weighted exponential smoothing of the gradient and gradient square. And basically, that's what is it. And then we using a so-called calibrated or unbiased, and using this gradient, first order and second order, divided by is 1 minus beta 1 or 1 minus beta 2 here, and using that to calculate a so-called calibrated or calibrated gradient, and use the calibrated gradient to update my new solution. This was the original algorithm for Adams, and the nice thing is keep both first order and second order momentum. And first order represents the directions of the momentum moving, and the gradient information gets added into the to the first order, and also the magnitude of the gradient also becomes at the second order momentum, as if the gradient vanish at the very end, and then for the unconstrained optimization, and the increase of the second order momentum will kind of stall. So these type of things is actually very considerate, and the Adam algorithm also has a good convergencies, but somehow the Adams algorithm has very sensitive to the step size alpha, or the nu right here we using in the algorithm, and we show you. And for some of for our test function, Rosenberg function wasn't the fastest algorithm, most effective algorithm among the others. Today we're going to introduce a different concept using for update the second momentum. Last time we talked about two other enhancement or improvement. One is trying to using the Nestrov momentum to correct the first order momentum. The other method is called Yogi method. Yogi algorithm is trying to use the direction of the gradients and trying to correct the second order momentum. So those two improvements, one is trying to improve the first order momentum. The Yogi method is trying to improve the second order momentum. And we have shown that computationally for the Rosenberg function, and they are fairly efficient in that regard. However, today we're going to introduce another algorithm which is popularly used. This algorithm is also trying to update, change the second order momentum in that regard, and using an infinity norm for the update. Let's look at the what is the AdaMax algorithm. The AdaMax algorithm uses the same way to update the first order momentum in this regard. So the AdaMax algorithm was proposed by a Kigma from University of Amsterdam, and Barr and Lay from University of Toronto in 2014. This is the article they are proposing it. Here, the AdaMax algorithm, instead of update the second order momentum in equation 3, like we had it before, using exponential moving average, here is using an infinity norm. It chooses the maximum of the beta 2 times the previous second order momentum compared with the absolute value of the current gradient, the magnitude of the gradient. Since the concept is fairly simple, similar to using the square of the gradient, using the absolute value of the gradient to compare with the exponentially smoothed. So therefore, this is how they update the second order momentum in that sense. However, the update is almost identical to the original Adam algorithm, and we calculate a delta equals to the first order momentum divided by second order momentum. And we're using a step size. Step size equals to the alpha divided by 1 minus beta 1, which is a calibrated step size using beta 1. And therefore, we're using that as an update to from the existing solution to the next step solution. The articles in 2014 suggested that we're using alpha equals to 2000s and beta 1 using 0.9 and beta 2 equals to 0.999. So here we're trying to compare, and so this is a very similar implementation as the original alpha, and instead it's just using an infinity norm for calculating the second order momentum as well. So this part is straightforward. An update of the so-called RMS prop type of update over here is almost identical. The only thing is missing is they didn't have the calibrated V hat and S hat over here, or normalized in that sense. So here we're trying to show you the implementation. The same thing, we're using the Rosenbrock function as a test function. We plot the Rosenbrock function as we had it before, and plot the level set. Here we have the AdaMax algorithm, and it's very similar structure. I just took the Adams algorithm block and update how we did it for the second order. So I still have the code from before. This is the Adams update, and here what we have is I just update the second order momentum using infinity norm. Okay, choosing beta 2 times the previous momentum, second order momentum, compared with the absolute value of the current gradient, whichever is larger, and we're using that as the second order momentum. Okay, and basically the structure is exactly the same. I'm not going to repeat too much of the concept. And here we have the main program. I'm still using the same seed as suggested, and alpha, our unnormalized step size is 2000th, and beta 1 equals to 0.9 as suggested, beta 2 equals to 0.999 as suggested, and we run it and to solve this problem. And this AdaMax algorithm actually solved the whole thing in around 40 iteration, and we get kind of lucky. And the solution quality is very good. And okay. And the execution time is reasonable, about 5,000ths of a second. So it's very low. Next, we're going to see the trajectory of the solution process. And this time I'm using just a square function, x squared plus y squared. I'm trying to using the same algorithm, cut and paste without the termination condition in the bag. okay, and all the premature termination condition. I'm just going to let it run so we can see how the algorithm converge. Still, initially, I'm using the 0.2 as the original 0.02, and let's do this, and using beta 1 as a 0.9, as suggested beta 2 as a 0.999. I'm going to run this. I'm running for 60 iteration, and we're just trying to show you how, and this is converging pretty smooth, and this is the initial point, and converging to almost the centers of that is also 0, 0. And see if we can increase the step size to 0.2 instead of 0.02 and see what happened. And you will see some kind of zigzagging. So step size is bigger in that sense. So it kind of giving you a circle around. See if we can increase a little bit more. Okay, so why don't we do this? 1.2. Running for 60 iteration, and you see that the zigzagging, the once the step size is bigger and the overshoots start happening, but still eventually it will converge to the optimal solution, and with the fairly accurate solution. So I just want you to see the the possible what is the effect for the step size to the AdaMax. However, my experience with the step size alpha, actually, it's not that sensitive. If you see, I'm using the original suggested 0.002 for 60 iteration, it's not converging that fast. Okay. So if you're using a smaller step size, in a sense, and you will get a slow convergences, but it's very consistent and smooth path, okay? And objective function always decrease at each iteration. But if you're using the larger step size, it will circle around to the optimal solution quickly, but convergence is still taking some step to get to the optimal. So there is the pros and cons to using larger step size, and also there's the pros and cons to using step size as too small. And this pretty much conclude this lectures, and because I want just have a quick introduction about the AdaMax. AdaMax is also fairly popular, implemented in both TensorFlow, deep learning AI library from Google, and also implemented as well, very popularly used in PyTorch, which is a Facebook version of deep learning platform. So many other platform also using the AdaMax, but and his performance is fairly stable. It's less sensitive to the step size compared to the original Adam algorithm. So it becomes more and more popular for people doing neural network training, because its methods actually less sensitive to the step size alpha in that sense. All right, I will conclude this set of the lectures, and we'll see you in the next lecture video. Bye-bye.